Hello everyone, welcome to the second part of the third lecture. I hope you had the opportunity to go through the first part of this lecture. Let's have a recap of what we learned during the previous lecture before we start with the new material of this lecture. So, during the previous lecture, we learned how to represent a complex number in a complex plane and how the polar form of this representation can be used to our advantage in understanding or in developing the mathematical model of a dynamically vibrating system. Then I referred you to a YouTube lecture on Taylor expansion. I hope all of you had the opportunity to go through the lecture. It's a really useful concept. And then based on um, the Taylor expansion and polar representation of complex numbers in complex plane, we derived or we proved the Euler's identity. Then we developed the differential equation of motion of a single degree of freedom system that is freely oscillating, meaning that there was no external force applied on it. Then we started off with the development of mathematical equation for a system that had no damping as a first scenario. So these are all of the slides that we went through to derive the equation of motion of a single degree of freedom system without any damping. So the equation that we derived was u as a function of time t is equal to u naught cos omega t plus u dot naught over omega sine omega t. U naught is the initial displacement of the system at t is equal to 0, and u dot naught is the initial velocity of the system at t is equal to 0. Omega was the cyclic frequency or natural cyclic frequency of the system. And then we looked into some other definitions of what a frequency of a system is, which is simply 2 pi over omega. And then we represented our equation of motion of a dampless freely vibrating system in the polar form in a complex plane using the representation on this slide. Now we finished off our last lecture when we were about to start talking about a single degree of freedom system with a finite amount of damping. As you will appreciate, this system is more realistic as compared to a single degree of freedom system without any damping, since nearly all of the systems or scenarios under consideration have involve structural systems that have finite amount of damping. So let's start this lecture from deriving an equation of motion of a freely vibrating system with finite amount of damping. From the last lecture though, I assume that you remember that our differential equation of motion of a freely vibrating system was equal to mu dot dot plus cu dot plus ku is equal to 0, and the equation of the solution of this second order homogeneous equation was equal to u is equal to g exponential of st, where t is the time period sorry, t is the time, s and g are constants. If we plug in this value of u into the above equation, we get ms square plus cs plus k into g exponential of st is equal to 0. Now, we know that g exponential of st cannot be equal to 0 for all values of t. Therefore, the term inside the round brackets has to be equal to 0, which is ms squared plus cs plus k is equal to 0. This equation was derived on slide number 6, and I labeled it as equation 2. This is the all-important equation that you will see um, that you see appearing again and again for different scenarios of a single degree of freedom system. If we divide both sides of this equation by m, we get the equation that is the first equation on this slide. Now, for this scenario, our c is not equal to 0. Therefore, from general equation of a quadratic equation, we get that the two roots of this equation are given by equation 4. So there can be three possible scenarios for from this point on for a system that has finite amount of damping. The first possible scenario is that the terms under the square root vanish altogether, and when this happens, we call the system critically damped. The second scenario is that the terms inside or under root in equation 4 are negative. This is this systems with such a property is called under critically damped system. And the third scenario is when the terms under the root of part of this equation are positive. That system is called overcritically damped system. Let us first consider the scenario of a critically damped system. For this system, the terms under the square root should vanish. That means that c over 2m squared should be equal to omega squared. Omega is the cyclic frequency of our dynamically vibrating system. Taking square root on both sides, we get c is equal to 2m omega, and we define 2m omega to be the critical damping of a freely vibrating system. So that's why you see a subscript cc. Now, for this scenario, our S1 and S2, which are our constants that we wanted to evaluate, are both then given by minus Cc over 2m. And if we plug in the value of Cc, which is 2m omega, we get S1 and S2 is equal to minus omega. So for a critically damped system, the value of the two roots of equation 4 both give the same result. Now plugging in the values of s in the above equation gives us this equation 4. Note that the equation contains no iota terms. Also note that since the root s1 and s2 were identical, the second term contains t in addition to g2. G1 and G2 were the two constants, and now the problem is to determine G1 and G2. The values of G1 and G2 can be calculated by considering boundary conditions. Let's do that. So the initial displacement of the vibrating system would be U naught is equal to G1 plus G2 into 0 into exponential of 0. This is equal to G1. That means G1 is equal to U naught. Let's take the derivative of equation 4. If we do that, we get, let's first open this expression, G1 into exponential of minus omega t plus G2t into exponential of minus omega t, plugging in the value of G1, which is U naught. We get U naught exponential of minus omega t plus G2t exponential of minus omega t. Now this is my equation of motion. Let's take the first derivative of this equation with respect to time t. We get the equation of velocity of our freely vibrating system. Once we do that, we get U dot naught, which is the initial velocity, is equal to minus omega U naught exponential of minus omega t plus G2 into exponential of minus omega t, and I will be continuing this in the second line, so it will be a little bit messy, but I understand what you will be able to. You will try this on your own. And my second will be omega t exponential of minus omega t. Now at t is equal to 0, again we will have U dot naught is equal to minus omega U naught exponential of 0 plus G2 into exponential of 0, and since the second term contains t, it will be equal to 0. And if I solve the above equation for G2, what we will have is G2 is equal to U dot naught plus omega U dot. Plugging in the values of G1 and G2 in equation 4, we get ut is equal to U naught plus U dot naught plus omega U naught right into t exponential of minus omega t. I can rewrite this equation as u naught 1 plus omega t u dot naught t into exponential of minus omega t. So this is what we have on the next slide, that is this equation. The only typo in this equation is that instead of a minus, there should be a plus here. And if we plot this equation as a function of time t, we will note that this system will never oscillate about its equilibrium position, um, except if the velocity and displacements are different in direction. That is, for if the velocity and displacement have the same direction, then this will never cross the point of equilibrium. But if they are opposite in direction, so for example, if we have something like this, it will cross it only once. This in effect gives us the definition of critical damping, CC. Critical damping is defined as the minimum amount of damping that will prevent oscillation of a system about its point of equilibrium. And that value from our previous derivation is 2m omega. So from having no damping in our system to having critically damped response, we have now successfully derived the equation of motion of a single degree of freedom freely vibrating system under two scenarios. Now let's consider a scenario where the terms under the radical do not disappear but are negative. That is, the damping C in the system is less than Cc. Such a structure is termed as undercritically damped structure. Nearly all of the systems that a structural engineer encounters are critically damped structure. Now from the previous derivation, we know that to determine our constant S, we had a quadratic form of the to solve, and since in this case C is less than Cc, we will end up with the terms under the radical as well as the iota, and there will be two distinct roots of this equation. If we define the damping ratio to be the ratio between C and Cc, then this equation, which describes our two roots of the constant S, can be easily written as C over Cc into omega plus minus omega iota into 1 minus C over Cc squared. Or in other words, our damping ratio plus minus iota into 1 minus damping ratio squared whole multiplied by the natural frequency of a dampless, equivalent dampless vibrating system, omega. So um, note the definition of the damping ratio in this lecture, and this is very important and a key term that you will encounter again and again and again. All under critically damped systems have a damping ratio less than 1. Okay, and that's why they oscillate about their equilibrium position. So if we plug in these two values of our constant S back into our general equation shown on this slide as this equation, we get this equation. But since I have jumped many steps ahead, we have missed a very important definition again. Our roots of the quadratic to calculate the constant S were expressed as this in the last slide, except that I missed the negative sign in the last slide. Now if we define the natural frequency of a damped system as Wd or omega d is equal to omega into 1 minus psi squared under the root, then the two roots to calculate the value of S can be written as this equation: S12 is equal to minus psi times omega plus minus iota omega d. And we need to then plug in the value of S into this equation to arrive at the general equation of solution of the differential equation, which is this equation right here. Now, doing all the algebra, and we can take out the exponential of minus psi times omega t out of this equation, and that leaves us with the terms that are shown here inside the square bracket. Again, G1 and G2 have to be complex conjugates of each other since the response has to be real. That requires us to then determine the value of GR and GI, which are the coefficients of the real and imaginary parts of these two imaginary numbers. And so if we plug in the values of G1 and G2 into the general solution of the differential equation and evaluate the values of Gi and Gr from boundary conditions, and then plug in those values back into the master equation, we end up with this equation that is shown on this slide. This is the equation that we all need to keep in mind always. Since most of the structures, or 99.99% of the structures that we encounter in civil engineering are under critically damped structures. So, another thing to note here is that this is a general form of the equation that we had derived for a freely vibrating dampless system. So for a freely vibrating dampless system, our omega d is equal to omega, that is damped natural cyclic frequency, is equal to dampless cyclic frequency, and our psi is equal to 0. If we plug in these two values back into the equation, this term becomes 1, this term vanishes, and omega d is equal to omega. So if I rewrite this equation for a damped system, this comes out to be u naught cos of omega t plus u dot naught over omega sine of omega t, and this was the equation that we had derived for a freely vibrating damped system. Again, we can represent this equation in the polar form, which is really useful if one is familiar with the concept of complex planes. And in the polar form, we note that the two terms in this equation, the first and the second term, are orthogonal to each other. So the second term, this term, is basically this vector, and the first term is basically this vector. Since, there needs to be a correction here. This has to be omega d plus u naught sine to omega over omega d, right? So the x component of this is nothing but sine of omega d, right? And the x component of the first vector is nothing but cos of omega t. And the total response is nothing but the sum of this component and this component. Okay, I messed up the figure, but you might need to rewind and recheck as to what I'm saying again. So how this then enables us to calculate our magnitude of the rotating vector. The magnitude of the rotating vector is nothing else but the Pythagoras sum of the two components, the two orthogonal components, which is the first component squared plus the second component squared under the root. The phase angle, that is the angle by which the resultant leads the trailing component, is then given by this equation, and this is actually similar to what we did for a dampless freely vibrating system during the last lecture. An interesting thing to note is that for damping ratio values less than 20%, the damped natural cyclic frequency over dampless cyclic frequency of structures tend to be more or less equal to 1. And this is really useful under certain circumstances, as we will see later. So if we plot the response of an undercritically damped system as a function of time t, this is how the plot looks like. Note that the envelope which envelopes the peaks of the response, right, the magnitude of the rotating vector is given by these dashed lines. And so the initial displacement is shown here, the initial velocity will be the initial slope of this line, and so on. This is a really useful sort of response for us to enable calculation of damping of a particular system. Remember from my first lecture when we talked about how damping cannot be calculated using the geometric properties of the structure, and how damping can only be measured. And I told you guys that we will be looking at as to how we could measure damping. What we can do is, so imagine that this portal is our structure. We can pull this portal towards one side or the other, and it will behave like this, right? And then we can immediately cut the rope of of the of the machine that is pulling this structure towards one side, and observe the oscillation of this structure. So if we observe the horizontal deformation of the structure, the plot might look like this. And once we have this plot, what we can do is we can monitor the response of the system at different peaks. And if we do that, and if we are using the polar form, then we will, um, I'm trying to remember the pen here, then we will end up with this ratio Vn over Vn plus 1. We can calculate this ratio, and we have, if we are using the polar form, we have this representing our response at a certain peak, um, and this is our response at the peak after that certain peak. So 2 pi, so n times 2 pi is the response at which we are monitoring the peak in the numerator, and n plus 2 pi is the response for which we are modeling our peak in the denominator. And if we do that, then we note that rho cancels with rho, right? And um, and so because cos of omega d, if we are monitoring the response at peaks, then cos of omega d and 2 pi over omega d plus theta will be exactly equal to this. They will cancel each other out. We are left with these two terms, in which, since these are exponentials, we can write this exponential as exponential minus psi omega n 2 pi over omega d plus psi omega n plus 1 2 pi over omega d. And if we solve this, we'll end up with this on the right hand side, noting that omega d is equal to omega times 1 minus psi squared, and taking natural log on both sides, we can define a logarithmic decrement, which is the decay in response, sort of the log of decay of response between two successive peaks, given by this equation 2 pi psi over 1 minus 2 psi squared. If we develop this further, for low values of psi, we can write the above equation approximately as logarithmic decrement, which is the decay of response, which is the ratio of response of a single degree of freedom vibrating system between successive peaks, is given by 2 pi psi. If we use the Taylor series, which can be used to open any expression on both sides, right, of the previous equation, we can get, and if we retain the first two terms, we can have, we can calculate the value of the damping ratio using this equation. This equation is nothing but the response of the peak response at cycle n minus the peak response at cycle n plus 1 over the peak response at cycle n plus 1 divided by 2 pi. This can be further simplified into this equation, and mm, the only difference is that the first equation is for peaks, for successive peaks. So n and n plus 1, but if you want to generalize it, and if you want to measure the decay over several peaks which are m cycles apart, then the second equation can be derived. So now we have a way to um, measure the damping ratio of the system, from which we can then calculate the damping of the system itself, since damping ratio is nothing but C over Cc and C over 2m omega. So if we know the damping ratio, and if we know the mass and the natural time period of the structure, we can calculate the C also. Okay, so as a rule of thumb, you know, for damping ratios between 10, 5 and 2.5%, the amplitude of vibration reduces to 50% after first, second or fourth cycle respectively. And this is just a rule of thumb, and it's a good thing to remember. With this, we have not yet considered a scenario where C over Cc is greater than 1, which is the case for overcritically damped structures, right? And the equation of motion of overcritically damped structures is actually derived similarly to the equation of motion of a undercritically damped structure. The only difference is that for undercritically damped structure, omega d was equal to omega into 1 minus psi squared, whereas for overcritically damped structure, omega hat is equal to omega into psi squared minus 1. And the equation of motion, rather than using omega d, we have omega hats in this equation of motion, or the general solution of the differential equation of motion. The resulting, so the values of A and B can be evaluated from the initial boundary conditions, and they come out to be equal to A is equal to U naught and B is equal to U dot naught. Note that the motion of over-critically damped system is similar to the motion of critically damped system, except that the return to zero deflection is slower. So with that, we have derived equations of motion of freely vibrating dampless and damped systems. In total, to summarize, 4 equations were driven. The first equation shown on this slide is for a dampless, freely vibrating system. The second equation of motion is a equation that is for a damped or critically damped freely vibrating system. The third equation is the most encountered scenario, and it gives us the equation of motion of a undercritically damped system. And the response of the undercritically damped system decays exponentially. Um, the equation of motion of an overcritically damped system is given by this equation. It's rarely encountered. I have yet to encounter a system that was overcritically damped in my career yet. So with this, we end up with our lecture number 3, and so we have successfully gone through all of the derivations of equations of motion. I strongly suggest that you open pencil and claw and you understand these derivations from that book. If there are any questions, we are going to have office hours next week, and I'll be glad to answer those questions about derivations. I might, if there are a lot of questions, I might derive them by hand and upload my derivations on the class work website. I will aim at presenting some numerical problems to these lectures, since I strongly believe that practicing the equations and practicing the concept makes all the difference between retaining these concepts for the long term or not. So with this, thank you very much and see you next time.